We have here three examples of some hypotheses. We have our null hypothesis and our alternative hypothesis. Here we're stated that the population mean is equal to 10 in the null hypothesis, and the alternative hypothesis is that it is not equal to 10. Now let's just go through a little bit of logic here and think about what happens with these different types of hypotheses. So we're hypothesizing that the population has a mean that is equal to 10. And we're going to test as to whether or not it differs from 10. If it's not 10, well, less than 10 or bigger than 10 is not 10. So this would be a two-tailed test. We would have some critical values here. And depending on what we know about the population standard deviation, these could be Z or T critical values. Just for right now, let's put T. And then we would have an alpha level of, say, something like 0.05 or 0.10. And since it's a two-tailed test, alpha over 2, 0.025, would be the area in each of these tails. Now we are going to take whatever measures we get from our sample, and from that sample we are going to calculate a test value. And if that test value lands in these rejection regions, so either way up here or way down here, then we would reject the null hypothesis. So if our t-test value is greater than the positive t-critical value, or if that t-test value is less than the negative t-critical value, and by the way, since the normal distribution is symmetrical, then these would be the same in their absolute value. So we can say t-critical or negative, or the opposite of t-critical. If either one of these things happen, then we should reject the null hypothesis. We should reject that the mean is equal to 10 and conclude that it's not 10. Now, we're going to talk about something else here called the p-value. The p-value is the area outside of the test statistic. So, what does that mean? Well, let's draw another curve here that we have a little more space to draw in. And let's do this two-tail thing again. So let's say we have critical values here. And the test value winds up out here somewhere. Well, the area then outside of this test value would be the p-value. Now, in this case, since it's a two-tailed test, then that p-value then would be doubled because it would represent this area that has been split out into two tails. But we notice that this area, if we're in a rejection situation where the test value would lead us to reject the null hypothesis, whenever that happens, notice that this p-value would have to be less than alpha. Alpha is the area outside of the critical value. So if I land out here, then this p-value is going to have to be less than the area outside of the critical value. So whenever we reject the null hypothesis, something else that would happen is that the p-value would be less than alpha. Let's look at another example. Let's look at this one here where the hypothesized mean is 50. Notice this time that the alternative hypothesis says that the mean is greater than 50. Now let's think about if we draw a sample, a random sample, and the sample measures put the sample statistic way down here to the left, then the sample wouldn't even support this alternative hypothesis. So we wouldn't even bother doing a hypothesis test. The question becomes, does our sample statistic land far enough out here to the right? It's only to the right that we would care then. So does it land far enough out here to the right so that it's significantly greater than this hypothesized mean, so that we would conclude that the mean is greater than 50? So again, we'd have some critical value, and then we'd get a test value of some sort. So let's say that this time the test value is here. Now notice in this situation, we would not reject the null hypothesis. And that is because our t-test statistic would be less than this t-critical value. It didn't land up there in the rejection region. Well, let's notice something else. This is the p-value, the area outside of the test statistic. And in this case, the p-value would be greater than alpha, because alpha would be this area here, where we have an area to the right of the critical value. So notice again that these things go hand in hand. If our test statistic and our critical value do not lead us to reject the null hypothesis, then neither is the p-value in alpha. So what we're seeing is that we have two ways of conducting these hypothesis tests. One is to look at the test values and the critical values, and the other is to look at the p-values. And we're noticing now how this works. When the p-value is less than alpha, we should reject the null hypothesis. Otherwise, do not reject the null hypothesis. All right, let's look at this example here. So here we're hypothesizing about whether or not the mean is 100. This time, the alternative hypothesis, or the claim, is that the population mean is less than 100. So we don't care about the right side this time. If our sample mean is greater than 100, then it wouldn't even support this claim. So our entire rejection region, alpha, is going to be out here in this tail, in the left tail. So let's say again that we have a t-critical value here, and our test value is here, our t-test value. Well, notice here that this area outside of the test statistic, which is the p-value, would be less than this entire area here, which is alpha. So in this case, the p-value is less than alpha, so we would reject the null hypothesis. Again, we are seeing that this method is consistent with whether or not the t-test value is less than the t-critical value in this left-tailed test.